In this video, we'll connect integrals and antiderivatives. This is the 5.3 pre-class video. Alright, let's start with the problem statement. Suppose the velocity of an object is given by v of t is equal to 1/2 t, and that's in feet per second. What is the displacement after 3 seconds? Let's make a graph of this, and note that displacement is equal to velocity times time, right? If I'm driving a car 50 miles per hour and after 2 hours, that means I've gone 100 miles, because it's velocity times time gives me displacement. But in this problem, our velocity is changing. It's changing as time goes on. Our velocity is equal to t divided by 2. But what we can do is approximate the displacement by putting 3 rectangles down like we've done before in other functions, and calculating the area of those 3 rectangles, and then adding them up. And the reason is, the area of each rectangle is a height times a base, which in this case is a velocity times a change in time. Each area of the rectangle is an approximation of the displacement of the object on that subinterval that the rectangle lies on. We can tell from the plot with the rectangles on it, that'll definitely be an overestimate, but what we could do is try doubling the rectangles. Let's do 6 rectangles. Each rectangle's area would give me an approximation of the displacement of a 1/2 second, but might as well get the exact area and do the limit as n goes to infinity. And we introduce that new notation in the last section. That'd be the integral from 0 to 3 of t divided by 2 dt. But in this case, we don't actually have to evaluate the limit because the area under the curve is a triangle. And the area of a triangle is 1/2 times the base times the height, which in this case is 9/4. But we have another way to find the displacement after 3 seconds because we know the derivative of position is velocity, so the antiderivative of velocity is position. So we take the antiderivative and we get 1/4 t squared plus c. Now that we have a position function, we can find the displacement by figuring out what's the position at 3 and the position at 0 and subtracting the 2. In this case, we would get 9/4 again. So we got the same answer doing it 2 different methods, and we should be thinking, I think there's a relation between finding areas under curves and antiderivatives. Let's look at one more example. Say we're trying to find the area under the curve from 0 to pi. So that would be the integral from 0 to pi sine of x dx. And this was defined as taking the limit as n goes to infinity of our function values times the delta x, sum them all up. But perhaps instead of doing that limit, which a lot of times ends up being messy, we could use our antiderivative to figure out the area under the curve, just like in that velocity problem a moment ago. So a good thing to be thinking about going into this next class is there actually a relationship between areas under curves and antiderivatives? But that's it for this video. We'll look at this more in class.